Okay, we are back to talk about the second law of motion, Newton's second law. Now I'm going to skip the Latin here, but I am going to go directly to the first translation, which says the alteration of motion is ever proportional to the motive force impressed and is made in the direction of the right line in which that force is impressed. I would not be surprised if you found that really confusing. This is written over 300 years ago, and that's the first translation of it. It does not translate that well into contemporary language. But let me just kind of read just a little bit more what Newton said. If any force generates a motion, a double force will generate double the motion, a triple force triple the motion. And so what he's basically saying is that force causes motion, but he says a little bit more than that. He actually says that an unbalanced force causes an object to accelerate. Now I know it's hard to see that there, but he said the alteration of motion, that is another way that they wrote that they would use the phrase for acceleration. So an unbalanced force, F, causes an object to accelerate, A. And that means if you apply force to an object and that force is unbalanced, meaning greater than any resisting forces, then the object will accelerate. You saw that in the lab we just did, that when you put the weight on the car that had a pulley with string over it, the more weight you put on it, the more it would accelerate. You definitely saw that. You also saw that if you increase the weight of the car itself, it had a smaller acceleration. Now here's Newton's second law in equation form. It simply says F is equal to m times A, or force is equal to mass times acceleration. The total or net force, that simply means how much force is acting on it minus anything holding it back. The total or net force equals the mass times the acceleration. We actually can put this in triangle form if we want to. F equals m times A, or A equals F over m, or m equals F over A. So yeah, force is mass times acceleration, or acceleration equals force divided by mass. Let me show you this. Kind of, again, this is what you basically saw. We have a car here. Oops, sorry, I went a little too far. Now I'm going to pull it back. There's a weight hanging here. And once I let go, you notice, hold on, wait for it. So you're going to notice that the car is basically going to accelerate. It's really hard to tell that. You saw it better in the lab. But the other thing you may notice is if I were to have no weight on here, basically it doesn't move. So couldn't quite tell that, but there it is. So there's no, that's a paper clip, but barely enough to make this thing move at all. On the other hand, let's say that I were to increase the weight of the car, the mass of the car. Now I don't know if you'll be able to tell this or not, but really hard to tell, but that's a smaller acceleration right there. Definitely smaller acceleration than just the car with no weight on it. So we are kind of seeing what's going on there with Newton's second law. Okay, mathematically F is equal to m times A. That's linear. It just means more force means more acceleration. You could also look at it in the inverse way, which says acceleration equals force divided by mass. First thing says more force means more acceleration. The next way of looking at it says the more mass, the less the acceleration is going to be. There's actually a brand new unit for this, and it's called, in honor of Newton, the Newton. The SI, or International System Unit of Force, the metric unit of force, is called the Newton. That is equal to a kilogram meter per second squared. Since F equals ma, the units for force are going to be equal to units of mass, kilograms, times meters per second per second. So it's meter per second squared, or kilogram meter per second gives us what we call a Newton. And that's just under a quarter of a pound. A Newton is not a lot of force. All right, a quick little run through some sample problems here. Let's say we have a 2 kilogram toy car. It's a pretty heavy toy car, but anyway, with a spring inside, and let's say the spring exerts a force of 6 newtons, and that's going to propel the car forward. What's the acceleration of the car? What would happen to the acceleration of the car if the spring force were greater? And what would happen to the acceleration of the car if you placed some small weights on top of the car before launching it? Acceleration of the car. Well, how do we get that? F equals ma. That's 6 is equal to 2 times a. 6 divided by 2 gives you 3 meters per second. And if you were to, if you made the spring force greater, of course the acceleration is also going to get greater. It goes up. And if you place some small weights on top of the car, that means you're increasing the mass, and the acceleration will go down. It is kind of intuitive, and again, it's what you saw in the recent lab. Problem number 2, what force is needed to make a 1,000 kilogram car accelerate at 2 meters per second Well, that's pretty easy. F is equal to m times a. That's going to be 1,000 times 2, which is going to be 2,000 newtons. Anyway, just to summarize, Newton's second law is the following. F equals m times a. The mass in kilograms is equal to, mass in kilograms times acceleration in meters per second gives you the force in newtons. Let's talk about a very special type of force, and it's the force that's due to gravity. We call it weight. It's a special kind of force that is important to mention here because it is so incredibly common. You have weight, then and the way you feel is, of course, due to the fact that we've got gravity on the planet, or pretty much everywhere. So we know that F equals ma, and if we let the acceleration due to gravity be g, then we get weight equaling m times g. So this is a little bit strange here, but this is the first time you're seeing a real difference between what we call weight and what we call mass. They're not the same thing, believe it or not. Weight and mass are not the same thing. The units for weight are still newtons. They can be pounds as well, but in the English or imperial units scheme. But weight and mass aren't the same thing. This also implies that weight can change depending on the value of the gravitational acceleration. If you're near the surface of the Earth, g is about 10 meters per second. That gives you your regular weight. You go to higher altitudes, your weight's going to be slightly less. Go to the moon, if we can only go to the moon, g is about 1/6 that of Earth. So let's say your weight's going to be 1/6 that of Earth. For example, if you weigh 180 pounds on Earth, you're only going to weigh 30 pounds on the moon. Your mass, of course, which is the amount of you, is going to be exactly the same. The amount of kilograms that you are is going to be the same. So your mass doesn't change, but your weight depends on the local gravitational field. Again, just to make a really strong distinguish between weight and mass here. Mass is the amount of matter. We compare that to the kilogram, standard. Weight is the gravitational force on the mass, and that's going to depend on the mass and the value of g wherever you happen to be located. So, an object that has mass, object's mass will not change, but the weight can be different depending on where you are. Most of the differences in weight tend to be very small, maybe not even measurable. Like if you were to go to the moon, it's a huge difference. But if you go to the top of the Empire State Building or the top of the Freedom Tower, g is a tiny bit less, several thousand feet above ground, but you probably wouldn't notice it. It could be measured. And certainly if you were on the top of Mount Everest, which is about 30,000 feet above sea level, you could measure that difference in g, although you probably wouldn't feel it. The bigger problem is that, of course, because g is smaller, you have thinner air. I like this picture because it's the same cube of aluminum weighed 3 different locations. We'll start off right here at close to sea level. It's actually giving you the mass in grams, but it's really measuring weight. It's just converting it to grams. So 295.21 is what it's weighing here at 300 feet above sea level. Let's go to 4,500 feet above sea level. Look at that, same block, less 294.99. Now that's not a huge difference. That's not even a full gram of difference, but that's measurable, as you can see. And over here at 7,600 feet, 294.93 grams. Again, not huge, especially from there to there, but it's measurable for sure. Just in case you're interested, there are actually English units of mass, even though we don't use them anymore. The English units of mass come about from the fact that weight equals mg, weight is in pounds, mass is something that we're going to see what the unit is in a moment, and g in English units happens to be 32 feet per second. The actual unit of mass in the English historical unit system is called the slug. In case you're interested in how many slugs you are, you take your weight in pounds and divide it by g. So g in the English units is 32 feet per second. So you want to find out how many slugs you are, take your weight in pounds divided by 32. Now, on the other hand, if you want to find your weight in newtons, that's pretty easy. Start with your weight in pounds, convert it to kilograms, just divide by 2.2, and then take your mass in kilograms and multiply by 9.8 or 10, and that'll give you your weight in newtons. And if you want to know your weight on the moon, just take 1/6 of the Earth weight, whatever that happens to be. Yeah, moon weight is kind of interesting. I've shown you some videos before, and I love this because they clearly have got a lot of stuff on their backs, which actually makes it hard for them to slow down, a la first law of motion. But look how they can actually jump higher than you would expect. So again, weight is subject to gravity, but mass is not. This is just kind of a relative chart that shows you the strongest gravity in the solar system is Jupiter by far. Next up, then you got kind of a four-way tie for almost first: Saturn, Uranus, Neptune, and Earth. Venus is pretty close to that as well. It's about 90% Earth gravity. And the smallest gravity, you got Pluto. I know it's not a major planet anymore. Mars and Mercury. So by comparison, if you were on Mars, your mass is the same. Let's say you're a 50-kilogram person. Mass is going to be the same. Your weight on the Earth will be 110 pounds. Your weight on Mars, less, 42 pounds. In case you're wondering, yes, you can simulate that by being in a dense pool of water, usually that has a bunch of salt added to it. So briefly about weight, apparent weight in a moving reference frame. We mentioned reference frames not too long ago, so I call this the elevator problem. Does your weight change in a moving elevator? Well, the short answer is actually it does. If your elevator is not moving at all, or if it's moving at a constant velocity, you would notice no difference in your apparent weight. You wouldn't, in fact, you've been in an elevator before and you haven't even been able to tell you're moving, I'm sure. Either you forgot to hit the up button or it just started moving. You were daydreaming and you forgot you were moving. So definitely when you're moving at a constant velocity, you can't tell. You know, it's like being in a car at a constant speed or in a plane at a constant speed. You can fall asleep. You really can. You can trick your body into thinking there's no motion. There's just no acceleration. Now, if the elevator accelerates upward and there you are standing on a scale, that scale is going to read more than your regular weight. We can calculate this. It's not too hard to do that. But if you're standing on a scale here where the acceleration is upward, you're definitely going to feel yourself pushed into the floor a little bit more. Again, that's accelerating upward, not moving with a constant velocity upward, accelerating upward. You don't do that too often in an elevator, but you do it all the time in roller coasters. And let's say that you're accelerating downward, which again, you don't do that too often in roller coasters, but you certainly can do it in amusement park rides. So if you're accelerating upward, you're going to feel heavier than normal. If you're accelerating downward, you feel lighter than normal. That's what happens when you are moving in a tall building with a long elevator and you feel yourself coming to a stop. It's almost like your heart's jumping out of your body. You feel yourself be a little bit lighter. And you've probably experienced the rides like a free fall ride before where you are on a tower, a drop tower, and you're belted in, but then they release you and then you fall at the acceleration due to gravity. We call that zero G, sometimes called microgravity, or the phenomenon is known as being weightless, which you can see here. Bouncing off. Now, they're not actually in space. They're aboard a plane. This particular plane is probably this looks like it's probably a NASA plane. It's where you can train for weightlessness. I have a whole lot of other videos. I've shown you some weightless videos before. That's just poor cats. I can't help but wonder if they let loose while they were in free fall. I don't think they would have liked this, that's for sure. I know cats, and I don't think any self-respecting cat would enjoy this. And there are another couple of videos taken. These are taken aboard the International Space Station, so they can give you some of the phenomenon of what it's like to be weightless. Doesn't mean you're massless. Weightless. That's a big difference. Okay, so we're going to be moving on to the third law of motion here shortly. But again, the idea of weightlessness means you have no local gravity, or you and your reference frame are falling or accelerating together. That's what it's like when you're on the drop tower ride at Kennywood, one of those 3 drop towers. You fall with the chair. So if you were actually sitting on a scale, you'd notice your weight would read 0. Okay, see you in a bit.